Hello. Hello. Can you hear me?
Yes, sir,
Yes,
you're
sir.
audible.
Yeah. So, before we start, any doubts, questions? So, I told you that we will be discussing some machine learning problem, but I decided that we will do it a bit later, maybe by next week, because there is some another topic that I need to cover for this course before I go into that part. So, yeah. So let me share my screen. Just 1 second. Yeah. Hello. Sorry about that. Hello.
Yes, sir.
Yeah. So we are studying. Today we will study the how to find the shortest path between two vertices. So basically, we have been given a G, okay, and we can also be given some set of weights, which are weights that are on the real numbers, which are on the edges. And if I take a path from U to V, so meaning it's like U, which is equals to say V0, then V1 up to say Vk, which is the V, then the weight of the path, so okay, this is a path, that means Vi comma Vi plus 1 is in the edge. The weight of the path is the sum of the edge weights. Vi comma Vi plus 1, where I equals to 0 to say k minus 1. Now, our job is that you have been given, what all things have been given? You have been given this graph, you have been given this weights, okay? And note that this is all of it can be given as an adjacency list, okay? It doesn't have to be given as the adjacency matrix. And you have been given these two vertices U and V, and your job is to find the path, the shortest path from U to V. Now, do you guys have any idea or how you can try to find it? I know some of you must have seen it previously in previous courses. Some of you might not, but
Sir,
I would still like to hear from you guys.
Sir, here shortest path means minimum weight path. Why
Minimum
are you
weight path.
considering the
Minimum
weight?
weight. Yeah. So yeah, among the set of all paths. Okay, so among the set of all paths that connects U to V. Okay, so it is the minimum. Path length, so weight of the path, so that the P is from U to V. The minimum of this. So in fact, it is called argmin. Argmin will give the path that minimizes it. So among all the paths that connects U to V, what is the shortest or the length of which path has the shortest or smallest weight? Okay. So how will you go about it?
Sir, we can find minimum spanning tree from the given graph.
You can find
By
a
using,
minimum spanning tree. Okay. So
but from that, any two vertices will have the shortest path. That is what I am thinking.
do you think a minimum spanning tree will give you
Yes.
the shortest path?
Means in that every vertex will be covered. The graph, all vertices of the graph will be covered, and the path between any two vertices will be the shortest path between those two vertices with minimum weight. If that's not the case, then it will not be a minimum spanning tree, right?
Okay, I am okay. So consider, okay, so think a little bit more. Okay, I mean, you are saying that you will first find a minimum spanning tree, right? And that minimum spanning tree will give you the shortest path between any two vertices. That's what you are saying. Hello.
Yes, yes, sir. Yes, sir.
No,
Yes.
sir, I don't think it is
Yes.
true.
So let's look at this graph. So just three vertices. This has weight 100. This has weight 100. This has weight 1. Okay, so say the U VW. What is the graph? What is the minimum spanning tree? What will be the minimum spanning tree?
So take the one weighted edge and any one of those 100 weighted edges.
Say I will take this one then and this one. It's a minimum weighted minimum spanning tree. Now in the minimum spanning tree, what is the distance between U to V?
100.
101.
101 if you use the spanning tree edges. But actually the
No.
minimum distance is 100.
Yes, sir.
So minimum spanning tree does not give you the minimum distance. Okay, this is a very important thing. It doesn't give you minimum distance between, or doesn't necessarily give you the minimum distance between them. Okay. But you have done something in the past. You have studied in some class, something which will give you the minimum distance, at least for some sense.
But we haven't considered weights there. In BFS, we are finding the statistic paths between vertices. If we
Good.
start with from U, then we can find the all the statistic paths from U to the vertices.
That's true. So you are saying that, so if you do BFS from U, and this is important, that all the weights are same, all the weights are same, meaning all the weights have say 1. So basically in some sense you can think of this to be unweighted, meaning if there is all the weights are same, then what is the reason of giving weights, right? So it's unweighted. Then you can compute, then BFS will, using BFS you can compute the shortest path, from U to V, right? Good. But if this is not a BFS, then if it is not unweighted, meaning the weights are different, then what will you do? Do you guys want to? So I just want to know how many of you have seen these things earlier? I'm quite sure at least part of it has been seen by people earlier. Yeah, maybe it's good to raise hands if you guys can. I can see one person has raised hand, so who has seen this one earlier? Oyonabo, have you seen this one earlier? Fantastic. He just, hello? Hello? Am I audible?
Yes, sir, you are audible. Oyonabo is like lost connection, I think.
Okay. So yeah, so I mean, the people who have not raised hand, can I assume that you guys have not seen it? Or you guys are just too lazy to not raise hand?
Sir, I cannot remember.
You cannot remember.
I mean,
If you don't
it's
remember,
No,
then
sir, it
that's
was not covered in, I think, any of the previous courses. So only people who had CS in UG might have seen this thing.
okay. Okay. And is there anybody who has done CS in UG here? In this
Only
class right now?
Saptarshi, I think.
I don't have, sir.
Saptarshi had raised hand.
Saptarshi has raised hand also, yeah. Okay, good. So if so okay, let me then go over it slowly. Okay, good. So if you want to now compute the shortest path between two vertices, now first of all, one thing is that this is an extremely important subject problem. Okay, why? Because this is something that is used by everywhere. So be it be systems, be it be machine learning, be it whatever. So it is because you want to compute, say for example, the weights can indicate various things, right? So weights can indicate the amount of time to compute some stuff, and that, so the minimum weight will be the shortest path to be taken from going from one computation to another computation, kind of stuff. It is used for infrastructure buildings. The shortest way you can say connect two objects, maybe shortest way of in networking and all. How do you connect two points with certain kind of wireless signals and all those things? So there are a lot of this kind of stuffs up there. Now there are more complicated stuff, not necessarily just finding the shortest path. There, how do you find shortest path such that the maximum, I mean, you want to also among the shortest path, you want to minimize the maximum edge weight, and so on and so forth. There's lots of different varieties of them. The simplest of them is this thing of how do you find the shortest path between two given vertices when there are edge weights. Now the edge weights can be positive, can be negative also. Many times negative edge weights are useful for, as I said, it's not just graphs that we are talking about, right? These graphs are used to model certain real life instances, and negative weights are many times used for exactly that purpose, right? So if you think of now solving this problem, that I have this UV thing, so somehow it is actually easier to compute, it's easier to think of what is known as the single source shortest path problem. What is a single source shortest path? It's like, okay, I wanted to know the shortest path between U and V, but instead I would find the shortest path or shortest paths in some sense from U to all other vertices. I mean, the main idea is just following, like if you have ever say tried to say go from one place of or city to another place and use Google Maps, right? And you can say, okay, how can I go there in the shortest time? Then the many times, I don't know whether you have seen this one, but the Google will give you some suggestion, like, so go walk up to that place, take this bus, and then wait for this much time, and another bus will come and take another train or something like that, and all, and you go there in say 40 minutes you are reaching there. So according to Google, Google has done something and found the shortest path. Now, but Google actually doesn't find the shortest path, because for Google's case, the number of vertices and number of combinations is so much. Google does some other local search kind of stuff like that. Okay, I mean, Google would not like to check that, okay, maybe to go from point A to point B, oh, I think this C is very far off. So for example, say if someone wants to go from say ISI to say Shialda station, okay, I mean, in that case, we should look at only the routes that goes through Calcutta. Why should we look at routes that goes to some different city? And Google kind of does that. Google will find out all the routes that goes from there to Shialda in various ways. But maybe, and this happens quite a few times, it is that, okay, the shortest path from going, or shortest time taken to go from say ISI to Shialda might be going through say a neighboring Howrah or something like that. So you take a longish detour. But if your job is just to optimize the short time taken, sometimes looking at a complete different point in the graph is useful. So in some sense, if you really, what I'm trying to say is that if you want to find the shortest path between u and v, we have to somehow check out, so to understand the shortest path between u and v, in some sense, we have to look at all the other vertices in the graph W and understand how much time does it take for u to go to W and from W to go to V, kind of stuff like that. In some sense, this has to be kind of solved. So I'm not saying that you have to do it all pair shortest path, but in some sense, to find the shortest path, you need to look at all the vertices. And that is why, to find the shortest path between u and v, it might be useful to instead in one go try to find out the shortest path u to any other vertex. Now, if that is the goal, I've changed the problem now. I made the problem harder. Your job is to find the shortest path between u and any other vertex. Now, how will you be able to do it? What would be your approach? Can you guys please, I mean, at least brainstorm something, think about some direction and tell me. Maybe it's wrong, maybe it's right, doesn't matter, but think about something and tell me.
So I have an idea that we can do BFS, and whenever we encounter a new vertex, we update that as the minimum of the weight of that vertex initially initiated to infinity set,
Yeah.
and the weight of the previous vertex plus the path taken to arrive at that vertex. So it would just whenever we are discovering any new vertex or revisiting an old vertex, it would update the length or the pathway accordingly. And so at the
It
end,
will
when
be
we-
updated, but will it be updated correctly?
Sir, if W is the vertex which going through every path between u and v, then shortest weighted path between u and v will be reduced to shortest path between u and W and v, sir.
So okay, so
If W is
that
the
is-
if W is the vertex which is in every path of u between u and v.
yes, so if W is a vertex that is in every path of u and v, then shortest path of u to v is the shortest path between u to W and W to v. That is correct, because if there is some other shortest path that also goes through W, that means this blue, I mean, either this part of the blue is more than this part, or this part of the blue is more smaller than this red part. So I will update the shortest path between W and V accordingly. So you are right, the shortest path. So it is a triangle inequality, right? In some sense, right? So the distance between U and V is less than or equal to the distance between U and W and V. And in fact, this you can say that, okay, and since all the paths goes through W, if you can assume that, then you are fine. But what if all the paths doesn't go through W? Right? That is, I mean, all the paths are not necessarily going through W. And Devarshi, the one that you told is when you are updating the
yes, sir. If no, like the previous vertex's smallest weight path can be updated later on, which would not reflect in the next vertex. So
exactly
that would not give the correct result. Yes.
right. Right. So let me maybe anybody have some idea. Sankalpa Roy, are you there?
Yes, sir.
Yeah, do you have some idea about how do you go about it? I mean, it's fine if you give a wrong answer, but you give me something. If I ask you to solve it, then what will you do? And how will you proceed? We give some answer. So Shankar, I mean, if I ask you to find the shortest path between U and V, if you're in a job and your boss comes and tells you find the shortest path between U and V, you will be basically quiet or you leave the job, is it?
No, sir. Say like we can denote the distances between the vertices with the edge weights, and then try to construct an say a MST which minimizes the distance, which is the edge weight, like that.
Okay, Shankar, when did you join this class today?
At 10-15 minutes ago.
10-15 minutes ago. So were you there when I think one of your friend told this MST thing, and we kind of went over the idea that MST will not give you a shortest path.
No, I heard Devorshi's answer.
No, not Deboshi's answer. So here was this example, I think, that we constructed at some point of time. This is just a 3 vertices graph with the edge weight 100 and 101. Now the minimum spanning tree will be the blue things, which will be basically this and this. But the distance between U and V, according to the MST, will be 100 plus 1, which is 101, whereas it would actually be 100. So minimum spanning tree does not give you the shortest path between U and V. Okay.
Okay.
So that approach will not give you that anything. So you have to come up with something. Minimum spanning tree is a slightly different concept than shortest path. Okay. Some other people, some idea? Shashwat Mondal? Shashwat Mondal?
Yes, sir. Yes, sir.
Yeah, you have some idea?
Sir, first, we should do one thing, that if we start from U, then we have to mark all those neighbors of U and then check their distance. And the formula which is written accordingly, we should update the weight, that if the direct path from U to V, the distance is smaller than via some middle vertex, that is W is written here, then we should update the distance between U and V with
okay,
that.
so Shashwat, so you know the solution earlier, right?
So I have some kind of idea.
You have some kind of
Not
idea.
fully.
But you know why are you doing it?
Just to take the minimize the cost.
Yeah, but why are you kind of following this particular direction? So let me give you. So okay, so if you know it, then it's hard to tip. If you don't know it earlier, I would like you guys to just think a little bit in the same spirit as we have been discussing other things recently. Namely, can you break this problem into smaller problems?
So we can look at the neighbors of V, right?
You can look at the neighbors of V, right? You have
And
neighbors
this-
of V or neighbors of, okay, fine. Say I have,
So
sorry, I have a graph, huge graph. Here is U and here is V, and you are looking at the neighbors of V. In neighbors
Yeah.
of V.
in neighbors,
In neighbors, the neighbors from which you are coming. Okay, fine.
and I'm going to think about the shortest path to these neighbors.
The shortest path between you to this thing, shortest path from you to this thing, shortest path from you to this thing, if I can find it. Yes.
How the shortest path would be the minimum of these things.
The shortest path between u and v. So say maybe let's call this one distance. Distance between u and v will be, so w1, w2, w say 3, the 3 neighbors, is the minimum over the distance between u and w plus the weight of w comma v. When look at all the w's which are in the in neighbors, which is we call the in neighbors of v, from which there are edges to w, basically v. So all the w such that is in the edge. This is a nice thing.
Sir,
Yeah.
instead of the idea that I suggested initially, instead of just doing BFS, if we can go by, I think it was in Prim's idea, I think, Prim's or Kruskal, I don't remember.
Mhm.
They choose the lowest edge path and then update, because that cannot be updated, that would not be updated later on. Again,
That
right?
is true.
Because
Good.
that is the shortest path. So
That
if
is
we
true.
keep doing that, I cannot figure the reduction exactly, but that would
So that
keep
is
the
also another
shortest
very
path
nice
assumption.
observation that you have done. So for example, somehow in this graph, okay, I want to find the shortest path between u and v, but forget v, we don't care v. Somehow some friend has come up and told that the shortest path between u and w is this. They have somehow managed to found it. So we know this thing. So we know somehow this is done, meaning this thing, there's no way I mean, I somehow luckily enough I found out somehow shortest path from u to w. Okay. Now, if I am talking about another vertex, say z, which is a neighbor of w, then the shortest distance of u to z, of course, it is less than the distance of u to w plus distance of w to z. This is something I know. This is also I know. Why? Because this is just the edge weight. And this is, of course, the shortest path between u to z passing through w. Right? So this is will give you the shortest path from u to z passing through w. So there's two concepts that we have here. You guys have told. One of them is, yeah.
Just one thing. This is this is not what I was saying, right? Like,
Okay. I mean, you are saying something similar to this. Just one step ahead. I'm actually one step ahead of what you're saying. That's all.
okay.
Yeah. You don't do a BFS, okay, but you do something very similar to what was done in maybe Prim's algorithm.
Yes, I was saying, how can we find the shortest path between u and w?
Yeah, that's this is so what we have done doing. So look at it. This is exactly what your friend has told. The shortest path from u to v can be reduced to finding shortest path between u to all its neighbors, right? And this is the opposite in some sense. You're saying, if I can find the shortest path from u to w, then this can be used to find the shortest path between u to z passing through w. I mean, these are kind of just the dual of each other. Okay. So one thing is, this particular thing can be made into a algorithm. Do you guys see this? This is something that is very much an algorithm thing. It might not be the best of the algorithms, but it's an algorithm. because to find the distance between u and v, I find the distance between u and w prime, u and w2, and u and w3, and something like that. And I have to take the minimum of them. Right? So that means if, and this, in this case, I know that this path should not be passing through v. I'm not interested in making it pass through v. So in some sense, if this takes t of n steps, to find this, it should take me just d of n minus 1, because I have made the graph smaller, because this is, I can tell this is in G and this is in G minus V. So I can write this whole thing as a recursive call. You guys see this? Thomas
Yes,
Kanti?
sir.
Did you understand? Thomas?
Yes, sir.
Yeah, did you follow? Okay. So if we do this one, can you write down what is the algorithm that will be? What would be the runtime kind of stuff? What would be the running time? So all that you say is that, okay, find the shortest distance between u and v is the, find the minimum over all the w such that w comma v is in the graph. The shortest distance between g minus v, in this one, the shortest between u and w plus weight of uv, no, not uv, weight of wv. And this takes, so how many of them should I have to do? At most n minus n of them. So this basically t of n equals to n minus 1 times t of n minus 1 plus, I have to take a minimum, so I have to take an order n. This is the worst case thing you can think of. So what is this runtime? Shubina, are you there?
Yes, sir.
Yeah, what is the runtime of this? How to solve the recursion?
Factorial n.
T will be basically something like factorial n, right? This kind of order of factorial n. So this is not good, not the best of the algorithms. But does it ring a bell at all? I mean, I don't know. So in room 520, how many people are there actually? Is there anybody there actually in room 520?
I think 520 responding via voice is not.
It's not possible, is it?
possible,
Okay,
yeah.
okay, fine.
Sir, I have one doubt
Yeah.
regarding this algorithm. Sir, in the above algorithm, what we are doing actually, in the final step, we are seeing the weight of the final edges possible, and then we are adding up all the paths that we are having, like W1, W2,
Correct.
W3, and then we are adding the weights of the last edges. But
Yes.
if there is no negative weights, then there is no actually there is no need of seeing all the things, right? Because if there is no negative weight, we can simply take the minimum of all the paths that we are coming through and then take the minimum weight. So it's actually doing greedy search in every step. Like if we can search the minimum path in every step, then we can come up with that. Yeah.
I mean, you are giving me an idea, right? How to solve it.
I'm giving an optimized way of not having the n factorial time.
Yes, you are correct. I'm going to come to that. You are very correct about that. But do you guys see that this n factorial? Just think a little bit here. Okay. I mean, I'm going to say what exactly Saptarshi told just now. But what is the problem here? Why did it suddenly blow up like this? Why is it runtime exponential like n factorial? What would be the next step?
Storing the shortest path, right? Like we are
No, storing the shortest path is not a tough job. Shortest path will be kind of at most n, size n. So it will be order n things, but we are talking about n factorial. So think in this graph. There is u, there is v, right? Say I have these three things: w1, w2, okay, and let me pass between w1 and w2. Okay. So when you are talking about this one, you will be doing d of g minus v of u to w1. You will be doing g minus v of u to w1, and you will also do d of g minus v of u to w2. But what is g of w1? How do you solve it recursively? Now in this part, there is an edge going from w2 to w1, so that means I will be doing d of g minus v minus w1 of u to w2, right? And d of here I will do d of g v minus w2 of u to w1, and now I have another edge like this, z. Okay, what will I do? What will the next step be? So when I have to compute in the d of g minus v minus w1, I have to do w2. W2 has a path to z, so I would be doing d of u v1 v2 u2 z. This will be a step that I have to do. I'm kind of opening up the recursive this tree, computation tree, right? And this will be v again w1 w2 and u to z. You guys see that this is how it, I mean, there will be other stuffs, but this will be there, a path of the recursive stuff. Hello.
Yes, sir.
You're seeing this one, right? So do you see what the problem is?
We are calculating many terms twice.
This
and
is being computed twice, right? Does it ring any bell to you guys? What happens when you do a recursion and then there is a thing that we do many times? Sankalpa are you there?
Yes, sir. Yes.
Do you recollect seeing this kind of a concept? What happens when we are repeating the whole doing the same computation multiple times? Like, come on, tell yes or no. If you don't see it, then don't say no, I don't see.
Yes,
No,
dynamic
sir.
programming.
Yeah, this is exactly dynamic programming. Correct, Tomasz. This was exactly what we have been doing for the last 4 classes. We had this exact same thing, right? When you have the same computation being done multiple times, then there is a way of saving it. dynamic programming. And basically you do the opposite direction. You go in the opposite direction. So instead of trying to break it up and writing it like this, you kind of go from the leaves in some sense, the shortest path, and store the data and move on, right? And what is the leaves in some sense? What is that? Here, what are the leaves things? It is the distance between u to w, where w is in the neighborhood of u. That's the kind of the smallest computation. Can I find out the shortest distance between u to w when there is a path from u to w? Not path, an edge from u to w? Of course I can, right? Can I? What do you guys think? I have a u and I have a h to w1, I have a h to w2. I know the.
I lost the connection. Can I just repeat the last part that you?
So I
After
want to
the
compute,
dynamic
say,
programming.
so you understood the dynamic programming connection,
Yes,
right?
yes, yes. After that, if you said anything. Yeah.
Yeah, so in a dynamic programming connection, how do you go about it? We want to solve the kind of the leaf computations in the beginning, right?
Yes,
And then kind
yes.
of produce it slowly from there.
Okay.
Okay, so now what are the leaf computations? So leaf computations is what happens the shortest things. Like, I mean, I kept on, you kind of keep on talking about dg of this kind of stuff like that and all, right? So it will come to this smallest one, like what is the distance between, so if u to w1, when the w1 is in the neighborhood of u. Can you compute it?
Just the distance between of the age between u and w1.
So you are
For
saying
this.
that the distance between u and w1 is equals to weight of the edge between u and w1.
So for the initial step, that's the
Yeah, first step. This is when I'm talking about when w1.
Yes, yes,
I mean u comma w1 is an edge.
yes.
Okay, so I mean u comma w1 is an edge. So this is what you are saying, right?
Yes, sir.
Okay, think a little bit. Can you guys think? Is this actually correct? You are making an assumption.
So what I was stating
Shortest
is
distance.
Shortest
that
distance.
if W1, like we have computed, suppose W1, W2, W3, these three are the neighbors of U,
Yes.
and say W1 has the least weight of
Okay.
all of them,
Okay, even then.
that
Okay, so
would
you are saying
surely
that.
be shortest distance.
Okay, so the least weight. So this, if you are saying that if d of u comma w, sorry, not d of, if weight of
Yes.
u comma w1 is less than the weight of u comma w2 and so on, say it's the shortest one, the smallest one, you can say that, right?
Yes. Yes.
Is this also
Because,
correct?
yeah. Because any path from U to W1 had to go through either W1, W2, and W3.
Yeah, you can go through say w2. Yeah.
Okay, we are considering negative weights, right?
Ah, good.
Okay. Okay. Okay.
So this is correct, but only if the weights are positive or non-negative. So see, you can have a negative weight, maybe, and there is an edge coming in somewhere in the, God knows, somewhere in a very weird place. Okay. Maybe to go from here to, maybe the weight of u to w1 is 1, maybe weight to w2 is 2. Maybe this to this vertex is 100. Maybe this to this vertex is 1000. God knows. But from this vertex to this vertex, the weight is say minus 10,000. So this edge is somehow hidden somewhere. And if that is the case, then how on earth can we say? So the shortest path between U to W1 would be then go through this, spend so much time, then be lucky enough to go through this huge negative weight and come to W, not the shortest path. So that is the problem. Okay, but at least we can say that if it is the positive edge weights, then we can say something nice, right? And let's start with that only. This is exactly what we will talk about in this class, rest of the class. When the edge weights are non-negative, then the initial computation can be done like this, right? And then how will you proceed? This is something that is the opposite of the proceeding that kind of we were doing here. It is kind of similar to when I was explaining you guys, when I think Akshay had given us this idea, and I kind of told you this thing going in the backward direction. It's kind of similar to that. See, what I'm trying to say is that this algorithm that I'm going to present, of course, you read it in a book, and the book will give you an algorithm and has a name, and somebody has found it. But if you think of it with a clear mind, by yourself, you realize that that algorithm doesn't come out of thin air. It was a step-by-step improvement. Okay, and this is exactly what I'm saying, that it's a recursive algorithm. And when you have a recursive algorithm, you see that there is a lot of computation being done multiple times. So you do a dynamic programming kind of stuff, which means that you first do the leaves, and now we have to combine them. And the basic concept is this, that I have this huge graph of G, and at some point of time, if there is a U, there is a set of nodes here. So this possibly contains W1, W2, W3, something. There might be paths to some of them, there might be edges to some of them, but these are I will color them, say red. So these are the nodes for which we know the shortest path between U and something. So we know. So what do we know at this point? We can think of. We know the distance between U and W1. We know the shortest path between U and W2. We know that shortest path between U and W3. We all know all of it. And now there exists a vertex, let's call this one Z, that is outside this. Okay. Now, how do I know the shortest path between U and Z? So it can be, look at the paths from U and Z. Okay. So the paths from U and Z would be, I will use a red color or maybe a green colored thing. They can be so you have to go from U to some vertex, say W1, and then cross this edge and go to V. So that means there is a vertex over here. You go from U W1 to this vertex and then go. Or from W2 you have another path. Or from W3 you have another path. In all of the paths, we can say that okay, it jumps over and comes to some new place. Maybe it's in some other vertex, from some another vertex here. So there is a vertex here. There is a direct path from this set, right? So now what I know is that, okay, do I know how to compute the shortest path between U and Z? Actually not, because I don't know the shortest path between U and this graph. I don't know the shortest path between say U and this vertex, and U and this vertex. I don't know shortest path between you and this vertex, but I know the shortest path between you and this vertex. So I know that if I have to pass through this vertex, then the shortest path between u and z would be how much? It would be the shortest path right now. The shortest path is u and maybe it's called W4 plus weight of W4 and Z. Okay, so this basically says that this is the shortest path between U and Z if we pass through W4. We can also find out the shortest path between U and this vertex. We can find the shortest path between U and this vertex, not shortest path, potential shortest path, right? So each of the vertex, these are the vertices that can be reached in one step from this blue color. So if I kind of define the blue color as the kind of whatever, in some sense, the boundary, which kind of says that okay, this is the boundary of the vertices to which we know the shortest path. Let's look at all the vertices that can be reached by a single edge jump from this blue boundary. Okay. And now every of the vertex I can put a weight here. So I can put a distance, say d1, d2. So these are the distance that would be, this is the distance if we say maybe there's a distance like this, okay? Maybe this vertex, there's a path from here to here. So there's a distance, and this distance is, we will maintain, is the shortest distance between U to D3 using the vertices inside the blue boundary. Okay. So at any point of time, we can maintain this thing. Once we know this particular blue boundary, we can find out the shortest distance between U to the vertices, which is just one step away from the blue boundary. And now, out of these DIs, consider the one that has the shortest, that is smallest. It is exactly what Devarshi was saying here. That if, so here the U is something, and you said, okay, if there exists if the weight of W1, if this is the shortest, this is the smallest weighted edge, then any other edge should of course cross through this thing. And since I know that 2 is more than 1 and there's no negative cycle, I cannot have a path from U to W1 which is cost more than the shortest path. Similarly here, if I take the minimum of all this distances and say, I said, okay, among all of them, say this, say this one, or maybe forget, yeah, maybe I said, okay, among all of them, this one is the shortest path, meaning this D4 here is less than D1, D2, and D3. So now what happens? That means if I want to come from U to Z, there are various ways I can go. I can go through W4, and then from W4 I can jump up one step and come to Z. That will cost me W4. Good. Now, if I want to go through to Z, there are other paths. Namely, I could have taken this path, or this path, or this path, or maybe even this path. But in all the paths, I have to go through U to this one and then to Z, or U through this one and then through Z, or U through this one and this to Z. But going from U to this vertex, already I have to spend D1 amount of time. The cost of it or weight of it is D1, which is more than D4. And since I know that there is no negative edges, so that means this path must be, so the weight of the path from U to Z via this vertex is more than D1, which is more than D4. So if I take the minimum over all the DIs, the vertex which has the minimum DI, meaning the vertex which has the minimum cost among all the paths that uses only vertices within the blue boundary, that vertex has to be, I can say the R. So that means this graph, there is no other path from U to Z that can take less than D4 amount of steps. So at that time, I can freeze this thing. I can say that, good. So now I know the shortest path between U to Z, and that is D4. And I will basically extend my blue vertex to include this, a blue region to include this. So, and this is exactly what will happen if you think of it. If you just think of this dynamic programming thing, and what was it coming out of it from going from the leaves to higher. Exactly, this is what is happening. This is exactly how this computation was done for the first leaf nodes, and this is how we continue. So in case you guys not understood it, so let me quickly go over some slides here that would help you to possibly follow it a bit more carefully. But is there any questions before that? I can, if there's some doubts, I'll be happy to. Yeah. So kind of to recap whatever we were doing, we are talking about the single source shortest path problem. And yeah, so of course, we are talking about the distance between any two vertices, that is the length of the shortest path between U to V. And that is what we are trying to solve, the shortest distance between, what is the shortest distance between U and V. Now, this is something that we just discussed in the beginning, that if there is kind of unweighted stuff, then you can do a BFS and you're done. But when you have a BFS, when you have weighted graph, then we have to think about something else, right? Like, okay, so here is an example of a graph with an weights. So there is a graph G to A, and we want to talk about the shortest path between G to A. And of course, there are paths of various lengths, and we want to find out the shortest path. And there can be negative edge weights also, in which case things can change. I'm going over this slides a bit fast because I think there's nothing much that you need to follow here. It's kind of some examples that are there about what is the shortest path between two vertices when you have negative edge weights. So, okay, first of all, I have not gone into this thing that what happens if we have negative cycle in a graph. I mean, there is another thing. So we can always assume that the graph doesn't have a negative cycle. So a negative cycle is a cycle whose sum of the edge weights itself is negative. It's not like just one edge is negative, but the sum itself is negative. And that is something you can always assume is not there. Why? Yeah, think about it. Why? Okay, because you will understand that if there is a negative cycle, then the problem becomes kind of too easy to solve. Right? Okay, so yeah, correct. So let me just go over all of these things. Yeah, so this is the thing that we were talking about, right? So you want to talk about find the shortest path between G to A. And one way to do it is this thing, the shortest path between, you do the recurrence, which is between, you want to find the shortest path between U to V in G. Is like you look at all the W's which is in the from which there are paths edges to V. Look at the shortest path between U to W in G minus V and take the minimum of that. This is exactly the recurrence that we kind of were dealing with. Right. And the correctness of this algorithm, I'm not going to go over it because you can see that it is kind of easy to see. And this is also, we have done that the running time of this algorithm in the simple case would be n minus 1 factorial. So, of course, we have to reuse the computations, and this is what we do. Right. So, for example, here, maybe let me just quickly forget all of these things. Yeah. See, here is this. So, this algorithm is what is called the Dijkstra's algorithm that I kind of described in the beginning and at the end. Sorry. So, I want to compute the shortest path between G and A. So, initially, to start with, I know what? I know that the shortest path between G and G is 0, right? So, I took 0. And for all the other paths, I have no idea whether they're even reachable or not. So, I put infinity. At any point of time, what I will do is that I will put a 0 and a value, a vertex number, a vertex label, which is the vertex from which the path comes. So you start with this, and the second row will be things for which I have got the answer. I have completely got the answer about what is the shortest path. So here at this point, we have certainly got the answer of the shortest path between G and itself. Any doubt? So I can put this G in this side. But once I put this G here, so I know the shortest path between G and itself is 0. Let's look at the two edges that goes out. Okay. So now that we have got these two things, that means to E, I can go from G, and the cost that I can incur right now is 9. Okay. And I can also go to F, and I can cost that I can incur is 11. Right? I have done that. Okay. Now this is what my answer is now. My state is that I know that the shortest path between the, from this set of all the vertices that are in the that have something in this second row, which is currently just G. Look at all the vertices which can be reached in just one move from one of those vertices here. And these are E and F only. Now, what can we say? This is exactly what Debashree was saying. That out of these two vertex, is it possible that there is a shorter path to F than just 11 length? Is it possible? Hello. Yeah, it's not. Somebody told no. Who told no? So you told that you cannot have a shorter path from G to F of length less than 11, right?
Yes, it is possible, right?
Yeah. So basically 9G for E it is not possible. Anything other than 9 is not possible for E.
Okay, for E it is not possible. Why? First of all,
It is-
somebody said that for F it is possible. What do we mean by possible? What do you mean by possible?
So, I said
If-
that for if it is possible.
Yeah, why is it
because
not? Why is it not? Why is it
up
possible?
to like we do not at this point we do not know what the rest of the graph is, right? When
Yes,
we're-
that's alright. We don't have any idea what the rest of the graph is.
So from E there can be say age of 1 to F that we do not
Right.
know yet.
It can be that there is an edge from E to F of weight 1. In that case, I could have gone from G to F not through this path, but through E, and that would have costed me 10. Shantanu,
Yes.
is this clear?
Yes. I have told to see all the ages and the weights.
Sorry.
I have considered that there is no age from E to F, so that's why I have told that.
No, but you
there
are
is-
taking for a particular example here, right? But
Yes,
I'm not
yes,
about a particular example.
Yes. Yes.
Okay, at this point,
Yes.
the only thing that we have seen is these two edges,
Yes. G to E.
G2E
the
and
rest of-
G2F.
We
We have
don't
no
know
idea
the
how-
rest of.
But now, Shantanu, is it possible that there is an edge from G to E, a path from G to E of length less than 9?
G to E, I have got 9, but if from other, if this graph contains no negative edge, so I have already got G to E 9.
Yes, but why
But-
can't there be some other edge, a path from E to G to E less than 9?
Yeah. If there is a possibility that G to F is 11, then there is some negative edge, -3 or
No,
that.
there is no negative edge. There is
Yes,
no negative
that's
edge.
why I am telling that there is no edge which is less than 9 of 8, 9.
There is no path. No, I don't get the answer exactly. I don't follow it. Why is
we can-
there no path from G to E of weight less than 9?
So suppose there is a path, like
Yeah,
then
yeah, actually, just one second. Yeah, you are right. You have understood that. Yeah, but Shantanu,
I am telling that if there is a path from G to E which is less than 9,
hmm,
so then I have to travel at first G to
some other vertex.
some other vertex, and
Yes.
G to some other vertex, and that vertex must be less than 9. Weight is less than 9.
Yes. And vertex must be less than 9. And that is
Yes,
not
but
possible
there-
because
That is
G has only
there is
2 vertices going out of it,
which is 11 and 9.
which is 11 and 9. Yes, exactly. Right?
Yes.
So that means right now we know that out of these two, E is something I certainly know the shortest distance. So what do? I say, okay, so I increase the blue boundary to E. And as soon as I make E in my blue boundary, you see there's some other vertices that I can reach very easily. So now, of course, I could have reached F from with G in one step. I can now also reach B, C, and D in one step from the set of vertices that right now has been colored red, say like in the bottom thing. Right? So how much does, so now what is the cost saying? See here, that is where this is important. I have added E, so the distance of G to E is 9. So I can reach B from E, and in that case the distance would be 9 plus the distance of G to E, which is 18, right? So in B I have written 18 and E. E is basically the vertex from which I have come. Similarly for D and similarly for C. Now at this point, what do you think? Can we say something? Can we say that there exists the shortest distance from G to, among these vertices, B, D, B, C, D, and F, 10 is the lowest, right? Is it possible that there exists that the shortest distance from G to C is 10 actually, or can it be lower than that? Hello, Sohan Das, are you there?
Yes, sir.
Yeah, so can you just try to see, to tell me, explain me, is it possible that there exists a path from G to C of weight less than 10?
No, sir. For this graph, it is
No,
not
no.
possible.
Forget this graph. For any graph with whatever information that we have got. Is it possible?
No, sir. Because we have to reach C through
We have to reach
the
C. The path has to reach C, right?
through the vertex E.
Not necessarily. Maybe, yeah, through the vertex. I mean, it has to pass through vertex C, yeah. But it can pass through like this also, right? C to D to A to C.
Yes, sir.
Yeah, then think a
Sir.
bit. At least tell me something. If you don't understand it,
Sir.
you have not, of course, opened your mouth also till now.
Weights are positive, so I think it is not possible.
Yes, but can you give me a proof of it? See, this is U, right?
Yes,
Okay,
sir.
G, whatever we are doing it. Let me just try to draw this graph. There are some other vertices here, maybe. So E and yeah. So see, this is what we have seen. Okay, so maybe there's an edge from here to here also. Okay. I have seen B, C, D, and F, and I know that to reach to B here, I take 18, C here takes 10, this 18, this takes 11. Now tell me, is it possible that there is a path from G to C of length less than 10? I know that this takes 9.
No, sir, it is not possible, but I can't explain.
You can't explain. Okay, do you want to try something? A little bit at least. I mean, it's not that hard, by the way. So you are in MTech CS or MTech CRS?
MTech CRS.
Okay, it's not that hard. How will you go from G to C? Since G to C has to, any path has to be like this somewhere here inside the blue edges, right? And then it goes out and then comes back to G. That is the only possible, right?
Yes, sir.
Correct. I mean, if you want to go from Calcutta to Howrah, there will be some place you have to cross the river.
Yes, sir.
Right? So this is the river. The blue line is the river. Okay. You know all the distance between your place and all the other places within this this place, within this river. Now to go from G to some place, there might be some path like this, and you say that okay, let this be the shortest path. So this is a river. You are crossing that river somewhere. How do you cross a river? How do you cross a river?
Sir.
You fly over the river?
No, sir.
So tell me, how do you cross a river?
We have to go through E or F.
Forget E or F. How do you cross a river in general? You take a bridge. This is the word that I was looking for. You
Yes,
cross
sir.
a bridge between 2 points. As I told you, you know the distance between G and this point. G and this point you know very well. Okay. and this point you don't know, but these are all the points which are just as soon as you cross the river, wherever you land, these are these vertices. Only vertices that has been managed to go, that you can go as soon as you cross the river. So here what is the river? Here, think of that there is a river around this one. You can see my cursor moving.
Yes, sir.
Think of there is a river like this. Okay. Now you are crossing that river. As soon as you cross the river, you land up somewhere. Which all places can you land in this graph?
We can go to D, B,
E.
or C,
Or F.
or F. Yes, sir. Also F.
Also F. Okay. As soon as you cross the bridge, you are hitting B, C, D, or F. Right?
Yes, sir. Yes, sir.
Now you can go. Your goal is to go various places. Okay. So your job is to go to Howrah station. You can cross the Howrah bridge, and that is fine. Or you can cross the maybe second Hooghly bridge and then walk up to Howrah station. Or you can cross the Bali bridge and then walk up to Howrah station, and so on. Right?
Yes, sir.
But right after you cross the Bali bridge, you realize that you have already spent 18 minutes. As soon as you cross the second Hooghly bridge, you realize that you have already taken again 18 minutes. Once you cross the, I don't know, some other bridge, you realize that you have taken 11 minutes. Then is it possible for you from any of these objects, any of the bridges, can you take any of these bridges and go to C in less time than what you could have done by crossing the Howrah bridge, which would have taken 10 minutes?
No, sir. It is not possible.
It is not possible, right? Because any path from within the river to outside the river has to cross some bridge, and right after you cross the bridge, let's take the time that is taken. And C says that, okay, that this place takes the shortest time. So it means now if consider this vertex C, to reach C, you can cross either the bridge right in front of it, or you can cross some other bridge and walk up to that place. But in that case, you have to pay the money for that to reach that point, right? And all of them are more than how much time you take for reaching C. Do you understand this?
Yes, sir.
So what can you say? What is the shortest time distance between G and C?
So we have to take minimum.
Yes, minimum of what?
Minimum of
Minimum of what?
Here we have to take 18, 10, and 18. Minimum of 18, 10, and 18.
And 11. Don't forget 11.
Oh, yes, sir. Also 11.
All of them you could reach by crossing a bridge. The minimum one, which is in this case C, for that we know what is the shortest distance. Okay. And we do that. And this becomes 10. Okay. Now let's look at it. So there was this B. So from C, I could have also gone to P now. So now I've got a new kind of our city has changed in some sense. Okay. Now the river now passes through this area around B, G, E, and C. And notice that all the other ones are reached by again bridge. And I have produced a new bridge, namely a bridge between C and B. But C and B, if I take this one, if I take this bridge, C and B, then how much time will I take to reach B? I will take the cost of crossing this bridge, namely 9, and cost of reaching C, namely 10, so 19. But I already know that there is a way of reaching B through E, right, which is 18. So why should I care about that? So I don't update this B. I let it be as it is. The next I take is again the same logic. Minimum of this 3 is 11. Right? And once I do this, you see that this D, now there's a different river. Okay. Now in the D, I have created another bridge from F to D. And that now if I can reach D from 2 places. Look at it. What was the earlier? I was reaching D from E, and that cost was 18. Now I can reach D from F also, and the cost will be cost of going through F and then going through D, which will be 17. And 17 is less than 18, and so I update it. And similarly, we keep on doing it. So let me ask you guys once, for all of you, did you guys follow this correctness of this algorithm? Okay, as expected, no answer.
Yes, sir.
Yeah, it's
Yes, sir.
See, if you want the formal proof line by line correctness, you will get it in any of the book. But I'm just trying to give you the intuition about what's going on in this algorithm. Okay. So what I tried to do is here, first of all, to kind of say that I hope that you guys will remember it, because it's like, and I've seen that some of you have seen it at some point of time and trying to remember, kind of memorize it or something. This such an algorithm, you don't need to memorize it. You know how the whole concept was developed, and everything will follow automatically. Okay. So this here is the pseudocode of the algorithm. I'm not going over it. I will upload this slide. If you want, you can go over it once. Now the running time of the algorithm. Okay, let's see. Every time we are adding one more vertex to the my country in some sense, right? One more vertex is pushed into the second row. So that takes, there are some V rounds. Okay, in some sense you can think of, because the V number of vertices, and every round one vertex goes from top to bottom, right? And every time I need to update only those vertices which are in the out degree of things that I've just added. So that's just DI of them, right? So if you see of it, you will realize that this algorithm will take order, and you take the maximum of them. The total runtime is just order V square, because every round you have to take this V of them, and you are updating that thing, and at most D of them, V of them, right? And you're updating that. So you can do it in other V square step. Now, so this is the what's called the Dijkstra's algorithm. Of course, it has a very nice name and all of them. You can do a even more cleverer implementation, which I am not going to go into this one at all, using something called a Fibonacci heaps, and there you can produce even for better algorithms like E plus V log V steps. So what we have done today here is that we have defined this we have given the Dijkstra's algorithm that finds the shortest path between a vertex and any other vertex. But remember this thing, this is only when you are guaranteed that all the distances are non-negative, or okay. If the distances are negative, then our algorithm will just collapse, because the whole concept of shortest distance being improved one by one, that is not working. Okay, that's just somehow not working, because I mean, Like here we are adding this thing. I mean, who told us that there is not a huge negative weight between A to E or something like that, right? So negative weight things is not, we are unable to handle them. So in the next class, before the next class, which is Wednesday, please try to recollect or try to prove for yourself. Okay, you don't have to read any book or something for that. I'm just saying, think about how can you handle the case when you have negative weights. How would you do it? It'll be exactly the similar idea. You have to break it up into smaller parts and then do something. But it will be a different kind of breaking up that we will do, not this particular breaking up. Okay, so any questions?
Hello, sir. Two
Yeah.
things.
Yeah.
First is you mentioned when mentioning negative cycles that it would be an easy problem, but wouldn't it like yield no, like there can be no specific result, right? Because we can traverse the negative cycle as many times as we want.
Exactly.
And,
So it will be minus infinity. It will be minus
yeah.
infinity. That's what.
Minus infinity.
Yeah.
And the second thing is that we in the class we have referred to some advanced data structures like Fibonacci heaps and union bound, even though these are not like would not be asked in the semester exams, but can we have an extra class or a tutorial specifically designed to discuss some of those advanced data structures that you feel are important?
See, we can do that. Okay, but honestly, there was I don't know how many people will be interested in that. As you can see here, also people seem to be interested in algorithms. It has a kind of a decaying effect. As soon as the results came out, there were people who were attending the class, and as the days are going by, this class size is shrinking.
Sir, I was also going to say that can you please take a tutorial class on the Fibonacci heaps?
So I think we can have one for CSCRS combined. At least I think there will be sufficient people, at least 10, I think.
Okay, we will see. We will try to, if I can take it, fine, or if not, I will ask the TS to kind of take one extra class on this Fibonacci heaps and all. Again, this is just for your knowledge. It's not a part of your class. The other thing that I can suggest is that if you guys are around in the summer, I would be happy to go over some of the data structures in the summertime, completely as the informal way of going over this stuff, instead of loading you within the semester time.
Okay, I think like that is okay for me, but Shoptorshi and I think some of the others that might be interested would be having summer internship. So we can have a talk within ourselves and let you know.
Yeah.
Yes. Okay.
Yeah, so that is something. Yeah, I mean this this data structure issues are that data structures can become very messy. So you have to be very careful about how do you handle these data structures and all. So it has to be done with a very particular. I mean, giving some high level picture is not exactly going to solve data structure issues. So if we are doing it, we have to do it very carefully.
Sir, we did this example for non-negative weights, right?
Yes.
But I don't think this will follow for negative weights also.
No, of course not. It will not. I'm not telling you the Dijkstra's algorithm solves for negative weight.
Okay, so we should assume that all are non-negative, right?
At this point, you can assume all are non-negative. This proof, this Dijkstra's algorithm only works for non-negative.
Okay.
Now, for negative weights, you guys think about how do you do it. Okay, I will come back next class and try to give you some ideas on that. Okay, but think about it. Exactly, it will also be a recursive algorithm. See, as I told you, recursion is possibly the most beautiful concept in algorithms. If you can master the concept of recursion, then you have mastered algorithms. Okay, so all of these things in Dijkstra's algorithm. The next thing we will learn is what is known as the There are some huge number of algorithms, by the way, for the shortest path algorithms. The Johnson's algorithm, Bell-Montfort, Floyd-Warshall, various algorithms, and all of them are recursive algorithms. Recursive algorithms of different kinds. So think about it, and you'll see how beautifully you can actually come up with some non-trivial.
So what if we add something to each edge? Like then add means the maximum negative weight we add to every edge.
Then then it will not work. Think about it. Why not? Think. Okay, there's a very good attempt, and it will not work. Okay. I mean, will the graph have the same set of? So you are saying add the maximum non-negative amount to every weight so that every weight become positive, and then you find the minimum weight, minimum shortest path. I claim that that shortest path will not necessarily be the actual shortest path. Okay, think about it. Think. Okay. Okay, good. I think let me stop here today, and we'll come back on Wednesday to discuss more stuff.